The beginning of Chapter 4 talks about calculus in 2 dimensions. Now that you know stuff about vectors, you are no longer limited to motion on a plane. For instance, here, now we can talk about motion in 2 dimensions. Now, if you'd like to think about multi-dimensional space, here I'm starting with just 2 dimensions, the x direction and the y direction represented by the I hat and the j hat. But 3 dimensions, you just add a k hat, and 4 dimensions, you just have an L hat. So the R vector, I believe, stands for resultant vector, because these are components that add up to a resultant vector, but this is really the 2-dimensional position vector. I've chosen some familiar equations for x position. This is just the position of something that is accelerating with an acceleration a sub x. 1/2 at squared, remember, is the constant acceleration motion in the x direction. But notice in the y direction, I just have constant velocity. This is v naught y, and there's no acceleration term. So this equation represents the motion of an object that is accelerating in the x direction, but moving with constant velocity in the y direction. In order to see what this motion might look like, let's add some numbers for the x acceleration and the y velocity. So let's say the object is moving with an x acceleration of 4 meters per second squared, but it's moving with a constant y velocity of 1 meter per second. Now remember, the object is just one object, and this is just its y component of velocity, and this is the x component of velocity, and really it's moving in 2 dimensions, so it's experiencing this acceleration and this constant velocity in the y direction simultaneously. This acceleration is only in the x direction, this velocity only occurs in the y direction. So when we plug these numbers in, our 2-dimensional position vector looks like this. So notice as time goes on, the x component of the position goes with t squared, and the y component of the position just goes with t. In order to see what this looks like, I'm going to need room for a graph, because I'm going to plot out the points for 0, 1, 2, and maybe 2.5 seconds. Now when I'm making a position graph, I can no longer use the x-axis as the time axis, because the x-axis is actually going to be the x position, and the y-axis is going to be the y position. So unlike in Chapter 2, where the x-axis was time, now the x-axis is in fact the x-axis in x position, and the y-axis is in fact the y position of this object that moves in 2 dimensions. So what I'm going to do here is I'm going to plug in values for time, and I'm going to start with 0. Notice at time equals 0 here and here, I get 0x position and 0y position. And so this object starts out right here at x equals 0 and y equals 0 at the origin. Now notice when I plug in 1 second here and 1 second here, I'll get 2 on the x-axis and 1 on the y-axis. And I had originally planned to plug in 2 next, but then I realized I didn't have enough room on my graph, so next I'm going to plug in 1.5 seconds here and 1.5 seconds here, and then we get this parabola shape. So notice as time goes on, this object starts out here at 0, then 1 second later it's here on this actual position on the xy plane, and 1.5 seconds later it's here. So between 0 and 1.5 seconds the object has moved like that, about that fast, maybe a little faster. So that's how this position vector in 2-dimension works. What it draws out is it draws out a map of where the object is at any given time on the xy plane. And notice you can easily extend this type of equation to 3 dimensions and even 4 dimensions, and if possibly you're a string theorist, maybe 11 dimensions. The interesting thing is that calculus also works in 2 dimensions. If we want to find the 2-dimensional velocity of this position equation, we just take the derivative like we would normally in calculus with one object added to another object, or one equation added to another equation, and we count the 2 and the I hat and the j hat. Those are just constants. So we know how to take the derivative of one equation plus another equation, and in 2 dimensions, that's exactly what you do in calculus. So if I want to take a 2-dimensional derivative of this position vector, I just take the derivative of 2t squared, which is 4t, and the derivative of t times j hat, which is a constant, which is just 1 j hat. And I get this equation for the velocity versus velocity as a function of time, except notice this equation is in 2 dimensions. Notice it's got a velocity equation in the x dimension that the x velocity changes, but the y velocity is a constant 1 meter per second. I hat and j hat, you treat them just like any other constant. They're just constant. They stay there when you take the derivative, just like the 2 stayed there, but the derivative of t squared is 2t squared, so I had a 2 times a 2, that's why this is 4t and it's not squared anymore. And these I hats and j hats, they just stay, you treat them like a constant, but that's how you take a 2-dimensional derivative. You just, the x component derivative and the y component derivative, and this is now a 2-dimensional velocity versus time equation. And how we use this equation, if we want to find the velocity in 2 dimensions at t equals 0, we just plug in 0 here, and we find out that the velocity at t equals 0 is 0 I hat and 1 j hat. What that means is that at t equals 0, the velocity only has a j hat component, it only has a y velocity, and so the velocity might look like this. It'll point straight up in the y direction. It has 0 x component at t equals 0, so it doesn't point left or right, it points straight up. And let's say to scale, this is how long the velocity vector is. That's 1 meter per second straight up. Now notice that's at t equals 0 seconds, we have a velocity of 1 meter per second straight up. Now you can imagine if I plug in t equals 1 second here, notice the x component will be 4 meters per second in the x direction, so the x component will be around this long. The j component will be still 1 meter per second up. So you can imagine that at 1 second, the velocity in 2 dimensions will be 4 meters per second in the x direction and 1 meter per second in the y direction, so it'll go up sort of at an angle, like this. What I want to point out here is that the rules of calculus made this a 4. This 4 had to be because of the power rule. It has to be 4t I hat, and because of the power rule also, this t becomes a 1. So the rules of calculus basically dictated that the 2-dimensional velocity equation for our 2-dimensional position equation has to be this. And in vectors, that means the angle of this vector at 1 second pretty much has to be this angle. It's got to be 4 over at 1 second, 4 in the x direction, 1 in the y direction. Notice at 0 seconds, the angle of this, according to calculus, had to be straight up. Now here's what's really cool. Notice at 0 seconds, the velocity here would be right here at the position vector 0 seconds. Notice that's where the object is at 0 seconds, and the velocity here, right at 1 second, would be right here. It turns out that calculus gives the exact right direction for the velocity of if you follow this path. Notice it's a parabola, so right here for an instant it's moving up before it turns to the right. Calculus gave the exact correct direction of the velocity if we match up to the velocity at 0 seconds right to the position at 0 seconds. Notice that right here the velocity at 1 second is, and we match it up to the position right there at 1 second. Notice if the object is really going along this path, the velocity right there is in fact pointed exactly at this correct angle that our velocity equation told us because of calculus. Isn't that amazing? It should just amaze you that calculus, not only does calculus tell you the velocity but from the derivative, but in 2 dimensions, calculus gives the appropriate direction for the velocity when you take the derivatives with vectors. Just to bring the point home, I'm going to plug in t equals 1.5 seconds. That's this point here. That's going to be 6I hat and 1j hat, which looks something like this. This is about 6, and this is about 1. And notice when I move this over at 1 second, it totally gets exactly right the correct direction of velocity right there. I mean, for every point, calculus gives the right direction in 2 dimensions that matches up with the two-dimensional position graph. I really liked math before I saw this in physics, but when I saw this in my physics class, it's just so wondrous. I mean, it's how does calculus know, because of the power rule, how does calculus automatically get the exact correct velocity in the right orientation that corresponds with each little place on a 2-dimensional graph? Now, notice that will work in 3 dimensions too. It boggles my mind. Alright, just to finish this out, I'll go ahead and take the derivative of this and find the acceleration equation. Notice the derivative of these 2 constants, 1j hat, those just totally go away. The derivative of a constant is at 0, and the derivative of 4t is just going to, this t turns into a 1, leaving just the 2 constants 4 and I hat. So notice the acceleration is constant. We knew it was 4 meters per second squared at the beginning, but notice also that it's only in the I direction. So the acceleration in all 3 of my time intervals, notice there's no t, so at t equals 0 it's 4I hat, at t equals 1 second it's 4I hat, and at t equals 1.5 second it's also 4I hat. So all 3 of those acceleration vectors are always all the same, and they just point to the right all the time, and so that's the direction of acceleration for this 2-dimensional motion equation. The acceleration, it's always accelerating along the x-axis, and it's moving with constant velocity on the y-axis. Notice that a curious thing is that the acceleration vector in 2-dimensional motion always points toward the convex side of the curve. That's just how it is. And so I'm going to leave you with this interesting idea, is that calculus, when we jump from 1 dimension to 2 dimensions, totally is internally consistent with how things really are, namely that if an object moves in a path like this and it's got this acceleration on the x-axis, calculus exactly tells you the right velocity at any given instant on the path of the motion, and it even tells you the direction of the acceleration on that path. So now, obviously, if that didn't happen, I would suspect that calculus is totally false. And yeah, you know me, I do have my doubts about calculus because of all that divide by zero stuff. That seems suspicious to me. But then calculus goes ahead and does this amazing and wonderfully consistent thing with the velocity that really makes me appreciate math. All right, and I hope you appreciate math in just the same way that I do, and have fun learning math.